manufacturers, the other one being the Energy Conservatory. So obviously I'll be focusing on, on our equipment, but really when it comes to blower doors, both brands work the same way. It's the same type of equipment. You know, one's Ford, one's Chevy, so just pick whichever one you like. But I'll be using ours as an example, just to kind of show how this equipment is set up, why we test, why we care about air tightness, what the equipment looks like, what comes in a blower door kit, and how you set it up, and then how you get the reading that you want to get. So with that, we'll get going. A little bit about myself. I kind of serve as Retrotec's in-house building science consultant. Used to be a HERS rater for an engineering firm in Raleigh, North Carolina called Advanced Energy. So I'm a recovering HERS rater, I guess. So I used to be in the field quite a bit doing this kind of thing. So let's start off with air tightness and why we care about this sort of thing. Why do we test houses for air tightness? Sometimes code requires this, or from a builder standpoint, it can be for quality control. If a builder says they build great houses, it's nice to have the papers to prove it, to go along with it. And it also, depending on how air tightness affects you, it really depends on what climate zone you live in. I live in the Southeast, down here in Wilmington, so we get pretty hot and humid during the summer. So humidity is a big thing that has a relationship with air tightness of the houses that we live in and that we build. It also depends on how stack effect is going to handle that building as well. So sometimes we run into different problems, whether we live in hot or cold climates. So one of the biggest topics when it comes into air tightness now is indoor air quality. It used to be all about energy. And so this is a nice little mock-up that my friend Joe Manometer built to show what kind of stuff can end up in a stud bay in an older leaky house. And obviously, as you can see, it's not very clean. This is Larry Zarker from BPI taking a nice whiff of what's going on in there. But if you think about the air you breathe inside your house, where does it come from? It comes from outside. And how does it get in? Through leaks within the building. And it brings other things with it: humidity, dust, pollen, sometimes pests, and whatever the pests leave behind, and on and on and on. So all those things end up in our lungs at some point. So indoor air quality has definitely been a hot topic, for the HVAC community, for the building community here for the past few years. And so air tightness plays a huge role in that, as well as keeping all kinds of pollutants out, keeping pests out, and things like that. So when we started, blower door testing, really back in the 80s, it was all about energy. We want to keep our energy bills low, and of course, we're still doing that. It's a huge benefit to making airtight homes. But chances are, if you're if you have an existing home that's having issues, chances are they're going to call to come to get help about comfort before they will energy. Comfort sells more than energy does. That's just what we've seen across the country. But indoor air quality is coming up too, just as important, especially for people that have COPD, asthma, things like that. Having an airtight, well-ventilated home really helps with those symptoms. And so this chart kind of breaks down where some of our issues come from and how they impact. So floors, walls, and ceilings, for existing homes, if we're going to try to patch stuff up, a lot of our problems are going to be solved at the ceiling and down at the floor if it's a crawl space or a basement. Duct leakage is also a part of our blower door number, so having tight ducts is important. People used to think it was windows and doors were the majority of it, but as you can see, that's about 20%. It's these other places that we can't really see with the naked eye, and that's why blower door testing and then having other tools as well, such as smoke emitters and thermal cameras, can really help us see where those issues are located. So when talking about air tightness of a house, we have to get familiar with this term called the air barrier or the pressure boundary, whichever one you want to call it. They're interchangeable terms, but it's basically that part of the house that defines inside from outside. It sounds pretty simple, but with more complex building types, it can be kind of tough to determine where that is, especially if you have a spray foam attic that may be adjacent to other vented attics. It changes. So it's important to know where that is, because that's the pressure boundary that we're actually testing. And that's where those problems are occurring. So if it's like your typical house with a vented attic, this blue line coming across here at the top of the ceiling is going to be our air barrier here. And so that's the ceiling drywall. But we also have to include everything that goes onto that. So if you think about all the penetrations that are in a ceiling, that's where problems are coming from. So if we have ducts in the attic, can lights, junction boxes, ceiling speakers, things like that, that's going to cause issues. And one thing, one of the leakiest parts of the house that people don't realize is where this drywall meets the top plate. And you have this crack down the middle here. And if you think about how many tops of interior walls that you have that are have hot attic space above it, that ends up to be quite a big hole. So thermal boundary, air barrier, whichever one you want to call it, it's good to get familiar with that and learn where that is on the plans and how that's going to impact the house when you run your test. This is a diagram we drew up when I was at Advanced Energy to kind of show where this air barrier is for new construction. We like to put it on the sheathing. So there's great products out there to help out with that, like Zip System. That'll actually help you build airtight walls. But then you have these transitions for windows and ceilings. And then the special points there where you have to pay attention to when you're air sealing that maybe products like that won't cover. And then as it transitions to the ceiling here, like I was talking about before, where your duct penetrations are, lights, things like that. So as you can see here, anywhere that there's a hole going through, it's going to cause a problem. Or if you're walking the house during framing and you can see daylight, chances are there's going to be an air leak there. It looks like they caulked part of the stud pack here, but then kind of gave up or ran out right here. So you can see daylight through there. So that's going to be a leaky point too. So, and this is the drywall to top plate connection that I was talking about earlier. So this picture is taken in an attic, looking straight down to the top of this wall. And we can see there's a pretty significant gap right here and on both sides of this wall. And that's pretty tough to go back and fix. The beauty of new construction is you have the opportunity to do this stuff right the first time. Going back in and fixing existing homes can be a bit challenging. So you can spray foam the entire roof deck, or you can do what they did here and actually seal that leak up directly. You can use spray foam, caulk. Seen people use bucket mastic before. But yeah, that's a pretty big leaky point in most houses that are out there that didn't have intentional air sealing during the design. Chases are another big thing. We can see this big opening here. Maybe they were planning to run a duct down here and then decided to move it. But these need to be capped and sealed. This is essentially like having a window open at all times in the worst possible place of the house. So that's another thing to pay attention to on plans, where these things are typically overlooked in traditional code-built homes. Corners, anytime one material meets another, that's going to probably cause an air leak there. So like caulking your subfloor to the bottom plates, caulking corners. This one's not caulked here, but this is a 2-stud corner, so hopefully it's caulked back on the other side of that one. Windows and doors, obviously, using low expansion foam there is a good option like they did here. I have seen some builders mess up and use high expansion fire foam, which will jam up that window and ruin it pretty much. So always make sure it's low expansion foam if you go that route. But if it's a tighter fit in there, you can also use caulk. Backer rod also works as well. And our mechanical penetration. So this is like if you stick your head halfway into a ceiling return, that gap there between the return box and the sheetrock there, that's a kind of a double whammy. That's duct leakage and envelope leakage all in one. So basically what that does, that return's pooling, it's pulling in air from the attic through that crack too. So that's not what we want. So we want to have a nice beaded caulk to seal that up, and same for the supplies as well. And bath fans, any type of mechanical penetration, you want to keep that sealed. Recessed lights, these are always fun to work around. If you get the airlock lights, they still do leak a little bit. What some builders do, they'll seal something like this, but you'll still get some leakage through that assembly. So I've seen some actually build a box out of either plywood or drywall or rigid foam and set over that can light and then seal around that and actually make that box part of the air barrier to move around it. So there's products out there too made just for can lights to air seal. So there's more than one way to skin a cat for sure. So that's kind of a quick and dirty rundown on air leaks in a house. So now I'll kind of dive into the blower door equipment, what comes in a kit, and how you set it up. So whether if you buy Retrotec or Energy Conservatory, when you buy a blower door kit, it's a calibrated fan. You have an aluminum frame assembly that expands into the doorway and a cloth to fill the rest of that in. And you get a digital manometer, which is what's going to give you your flow reading. So these are basically the essential components here. And with Retrotec, you have the option, you can do this frame and canvas, or we have these expandable hard panels that pop into the doorway. Both work great. It's really just personal preference. But the frame and canvas is what we typically see the most. Just they're less expensive, but some people like the hard panels because they look a little more professional. And with our frames, they just snap together on the corner. So they're numbered on each end. So you match a number 1 with the number 1 and go and work away until you have your rectangle built. But we have different ones. If you mainly work with super tight houses that are going for like passive house numbers, we have a small window frame. So you can actually test leakage in the doorways too. And if you're dealing with flows under 1,000 CFM, all the time, you can actually get away with doing your blower door test with a duct tester fan. And that's what this is here. And we have a canvas with a smaller hole for that to fit into it. So a lot of the guys that mainly test for passive house or mainly build passive house, sometimes this is all they use because that's all they need. They don't really need to generate much flow. But we also work on the other end too. If you have really tall doorways, like 8-foot doorways and stuff like that, that you build a lot, we have an extra large frame to fill those in. But yep, they pop together. And once you get this down pat, you can have a whole system set up in under 10 minutes usually.
Sam, do the hard panels leak less?
They actually leak a little more. It simulates a leaky doorway pretty much if it has like pretty poor weather stripping in it. But you'll probably get, I think it's 14 CFM more of leakage than the frame and canvas.
Thank you.
Yep. But that's what these look like. These are the hard panels. And so, yeah, where they leak are these seals where the panels meet. So we'll talk about how one of these works. So as I mentioned before, we have a fan that we set into this thing. And it actually has 4 little pickups. And the Energy Conservatory fans work the same way. So I think I have a closer, yeah, here we go. There's 4 tiny little holes here that pick up pressure, and there's an airtight tube that goes around the circumference of this yellow piece we call the nacelle of the fan. And then that ties into this yellow port at the top of the fan where your manometer plugs in. So what that's doing is reading fan pressure. That's how the manometer knows when your fan gets to 50 pascals, or when your house gets to 50 pascals of pressure. So no matter what house we test, if it's residential, we test at 50 pascals. That puts every house on an even playing field. And essentially what that's like is it's like a 20-mile-an-hour wind on all 6 sides of the house. So floor, ceiling, floor, ceilings, and all 4 walls. So, but on the other end, 1 pascal of pressure is a very small amount of force. So 1 pascal is equal to 1 gram over a square meter. So about what a paper clip does. It's actually a small amount of pressure. So if you worked in HVAC and you're familiar with inches of water, there's 250 pascals in 1 inch of water. So this manometer is what we're actually calling micromanometer. It's accurate within 1/100th of a pascal. So it has very, very granular sensors in there that are super accurate on this kind of thing. So that's how the manometer knows when the house gets to 50 pascals by reading that fan pressure. And it also has this red tube that goes through the canvas that reads outside versus inside. So that's how it's determining when that house gets to that point. Anytime you're using a manometer to read pressure, you're just reading pressure with respect to another area. So here it's outside with respect to inside. And then we call this a 2-channel manometer. So it's actually 2 manometers built into one. So it has channel A and channel B. Channel A is reading outside, inside. Channel B is reading your fan pressure. And when we get a blower door reading, we can interpret it a couple of different ways. What it gives you is the leakage in cubic feet per minute at 50 pascals. So usually when you hear a blower door reading, it's going to be a number and it's going to say CFM 50. So that's 1,000 cubic feet per minute at 50 pascals. Or we can do air changes per hour. And for that, you need to know the volume of the space you're testing. Not often is that going to be on the plans. A lot of times you just need to figure out what that's going to be. If you have some weird details or some vaulted ceilings or like that, it's going to take some extra measurement to figure out what that is. But you can actually enter the volume into the manometer, and that way it'll give you air changes per hour in real time. So that way there's no extra math needed. So depending on how you want to interpret it, the manometer will do it for you. So yeah, so there's basically 4 little pinholes in here, so it's important to keep those clean. Sometimes they can get gunked up if you test a lot of dirty spaces. There are ways where you can test to see if they're clogged or not. I've got some videos online on our YouTube channel on that if you want to look into that. But equipment maintenance is it's another hour-long discussion on itself. So this is essentially what we're doing when we test a house. We can test in either direction. But I like to test and to depressurize the house. You can either depressurize or repressurize. The reason that I like to depressurize when I can is because you're pulling bath dampers and kitchen dampers shut instead of blowing them out. So you'll actually get a little bit tighter number and not include those in. Some people get more detailed and they'll test in both directions and take the average. When we test commercial buildings, that's what we're required to do. But for homes, that depressurization number is enough to tell you what's going on. And that way you're not including those dampers that'll blow open. But with respect to outside, the house will be negative 50 pascals, which means right on the skin of the air barrier is a positive 50 pascals. So, and this is helpful because if we have another manometer that can read pressure, we can go around the house and look for pressure differentials to find leaks that way. So we can actually find leaks with a manometer that's just reading pressure on both channels. So again, that's another diagnostic we can talk about later on. But this is essentially what you're doing to the house. And again, it's like a 20-mile-an-hour wind hitting all 6 sides of it. So so what you're doing is you're exaggerating those air leaks. 50 pascals is enough pressure to balance out the house to see what's going on. So you're just artificially moving air through every leakage point, and the fan is able to calculate flow from that. And the reason that is, actually, I'll get to that in a second. So here it is, again, depressurizing versus pressurizing. You just flip the fan around. That's really all you do, and you run the test the same way both times. Just with pressurizing, you'll blow dampers open, and you'll likely get a higher number. So we'll quickly talk about setup, and we'll just do this with the frame. All of our products come with a hard copy quick guide on how to set up anything, whether it's a frame or a fan or a manometer. So again, like I mentioned, you just pull those frame pieces out. It comes in this little shoulder sling. Get your rectangle together. Again, they're numbered, so match 2 to 2, 3 to 3, 1 to 1, 4 to 4. And they just pop in like so, and you have a nice rubber seal all the way around. And it has these little cam levers on each piece, and so you just loosen those up, and that'll allow you to spread that frame out to fit the doorway. And then there's a cross piece. We give you 2. One is where the fan's gonna hang from, and then we have another one to give you extra stability towards the top. Last thing we want is that thing blowing out of there like a sail. So we want a good tight fit inside the door there. And then we get our canvas and just spread it out on the floor. And then it has these little Velcro tabs where we can fasten it into place. And then we pop it back into the doorway. And then we make sure everything's nice and tight. These cam levers, we tighten them down, hand tighten them down, and then you flip it and it gives you some extra tightness in the doorway there for a good snug fit. And you just do that all the way around and on both crossbars. And then we set up our tubing. So for our tubing, it all comes bundled together in one piece. We call it the umbilical. It's got your tubing, your data cable, and a charger cable for the gauge. With our manometer, it charges with micro USB. So just so you're not dead in the water, we put a USB port on the fan itself, so that way you can charge the gauge off the fan if you forgot to charge it the night before. But all that's bundled into one piece. But one piece is a red tube. So if you just remember, red tube goes to red canvas, and you just pop it through this little hole down there and throw it off to the side. And you want to get it off to the side at least 5 feet away from the fan. You just don't want the fan to affect it. You want this to read kind of a zero pressure outside. So
Sam, if you forget to throw that out, you can always do the crawl of shame.
The crawl of shame. Yep. That's just when you have to crawl through the hole yourself. And we've all been there. There's people who've done it and people who haven't done it yet. It happens to everybody. But yeah, this is how you don't want this cord set up this way, because that fan's going to manipulate the end of it. So you want to throw it off to the side, like in the second picture here. One difference that I need to mention that's different between the Energy Conservatory and Retrotec is if you're pressurizing with a Retrotec system, you do not need to add an extra tube from the outside. With the Energy Conservatory, you need to add an extra tube or your reading will be 20% off. And the reason that is because the fan is manipulating pressure inside the house, and so you need to cancel that out. With the Retrotec manometer, it actually feels that fan pressure on one of the open ports and then mathematically removes it. So that's one of the setup differences between the two brands there. But once we get to that point, we have this little shower cap cover. Both brands come with it. So we just pop it over the inlet side there if we're going to set up to depressurize. And then there's this little elastic hole. Again, both brands set up the same way. There's this lip around it, and it locks it into place. And then you strap the handle into the top just to hang it a few inches off the ground. And then for us, everything's color coded. So yellow hose to yellow port on the yellow fan. And then you put the other end on the yellow port on the gauge, and then, red to red. And then we have this data cable here. It's a Cat5 cable, and this allows the manometer to control everything. So there's a manual dial on the fan, but you don't really need to use it. You can just enter 50 pascals on the gauge and hit go, and it'll run the fan by itself. You just pop everything in like so, and the fan comes with this little pocket on the bar, so you can keep it up there and not have it lying on the floor or something. And of course, we got to have power. Plug it in the wall. If you get into any larger testing where you need more than one fan per circuit, or you're going to be tripping some breakers. And there's this green status light. So if that's ever blinking or red, and you have everything plugged up, that means your Cat5 cable went bad, or the gauge is not reading a fan. So as long as it's on, green, and steady, you're good to go. But if you notice that it's blinking or turning red, that means try a different cable. It just might need to be replaced. So that light does have some meaning to it. And then we're good to go from there. I'm going to talk about some house setup in a minute. Talked about that. Yeah, so the term Pascal is named after a French scientist, Blaise Pascal. And again, it's 1 Newton of force applied over 1 square meter. So very, very, very small amount of pressure.
Sam, I always like to say that one PSI is equal to almost 6,700 pascals.
Okay.
So it's like you said, paperclip, but it's enough to get a reading without damaging the house.
Exactly. And we'll get into this later, but yeah, I like to start the fan off at 25 pascals if it's a new house I haven't been into yet. And then just kind of walk around and see if there's any weird smells or anything like that. Make sure all gas appliances are off and things, and then start up. I did a test one time on a house that sat vacant for 2 years, and all the P traps emptied, and I didn't check them. And yeah, I did not have that fan on for very long. It was awful. So yeah, start off light, walk around, check for anything weird, and then once it all seems okay, especially houses with fireplaces that have been used, like if it's a wood burning fireplace and you're depressurizing, that's one of those instances where I like to pressurize instead and not pull that stuff inside. Another one, if I know there's mold growth on the air barrier somewhere, I don't want to depressurize and pull that stuff in. So pressurizing is a good point there. And then this is worth mentioning too, like if you're working with older existing homes, if you know that there's vermiculite insulation in the attic, do not run a blower door. That is the only time I say you don't run a blower door test. So there's actually a trust fund out of Charleston. I think it's the Vermiculite Institute or something like that, but they'll usually cover about half of the remediation to get that vermiculite out and better insulation installed. So
Sam,
if you come across that,
why it would be important not to pressurize. I understand why you wouldn't want to depressurize and pull all the friable particles into the air inside the house. So assuming that the attic's always open.
Even when you pressurize, you're going to disturb that insulation. And once it goes airborne, it can fall down through leakage into the walls. We just don't want to disturb it at all. And no matter which way you test, it's going to disturb it. So it's better be safe than sorry. That's our stance on it. But yeah, back to pressure here. Like I mentioned before, 248 pascals equals 1 inch of water column. So a lot of HVAC contractors don't really deal in pascals much. They're usually dealing in inches of water. So it's kind of a new metric for them to learn, but it's just a smaller pressure on a smaller scale. Let's see here. So this is if you look at the top of the manometer, that's just color-coded ports. So channel A goes to outside, channel B goes to the fan. And again, it's 2 manometers built into one. So there's a pressure sensor on both sides, and they're just working together. You just have to have all of that together to be able to get the reading from the blower door. And I pretty much covered this earlier. We tried to make this as easy as we can with the color coding. If people are colorblind, there's not much we can do about that. But we call it, we don't call it idiot proof, we call it idiot resistance. Some people still have screwed it up before, but we tried to make it pretty simple. So if you're looking at the gauge, channel A is here on the top, channel B is on the bottom. And so you can get different displays to come up here for channel B. You can have it read pressure on both channels, and you can have it read flow. But CFM is what you want it to read here on channel B. So this is if you're doing a blower door test and you're doing it right and it all falls within the fan's limitations, you'll have your 50 pascal reading here on top, and then whatever your flow is will be down here at the bottom. So that channel B is going to give you that magic number you're looking for. So that's just an example there of a test. So that house tested out at 1469 CFM at 50 pascals. You can also select your device here. So if you have multiple fans, this gauge will actually run Minneapolis TEC fans too. Or it of course runs all of our fans as well, duct testers, things such as that. So we tried to make this interface as simple as we could. So you just actually tap a picture of the fan, and it'll give you which range you want to set up. And then it'll also allow you to cycle through the different fans you can select. I've got other slides on that. So this is one of the most common questions we get for people that are starting out is, how do I know which range to go to? Like, how do I know where I need to be? Basically how this works is the larger or leakier the house is, the more the fan needs to be opened up. And then the other way around, if it's a smaller or very tight house, then you need to choke it down some. We have to do this because we have to maintain fan pressure within the shell of the fan here, so that the manometer can actually read pressure at the center of this fan, like I mentioned before. So if we have a really tight house and we're running it wide open, this fan is going to be barely running and it's not going to generate much pressure. So we have to choke it down and put a smaller opening on this. And the way that a blower door is able to calculate the reading to flow, if you know the pressure of the fan and you know the area of the hole size, which the manometer knows all of these on all of these settings, then it can calculate flow. And so it's just doing the math for you there inside the gauge. So that's how it's able to spit out the flow of the leaks throughout the house. So if I'm starting out with a new house and I'm not really sure what to expect, I always start with ring A. This B8 plate, we call it B8. We used to have more rings in our older models, but now we just have one ring and a plate with holes. This just sticks on magnetically, so it's super easy to pull off. And then these range plugs just pop in and out. And then there's pockets on the cloth where you can just pop them in there to keep them off the floor. So we did this design this way because there's no moving parts. There's no little tabs you have to move around that'll break off down the road. So it just tends to hold up longer. But I'll usually start with A if it's a house I'm not really sure what to expect. And then if I can't reach 50 pascals, then I'll open it up. Or if I'm not getting a flow reading, then I'll choke it down. And so that's usually a good starting place. If you're always starting with tight houses, then go ahead and just have the B plate in there. If you do super tight houses that usually come under 1,000, this B4 range is a good place to start. So, it's kind of like changing, depending on how fast you want to go, it's like changing gears in a car. You just got to find that sweet spot. So that's essentially how that works. So the leakier or larger the house, you have it open. The tighter or smaller, you have it closed. And again, if you can't reach 50, you open it up. And if you can't get a test pressure, you choke it down. And then we have this at feature too. And what that does is, say you have it open and you're running it wide open and you can't reach 50 pascals, so you get to like 45. What this does is it extrapolates the reading and just does the math for you and says, well, if we could reach 50, here's what the number would be. And this is only accurate within 20% of the fan's ability. So our Model 5000 will do a little over 6,000 CFM. So for example, like if you're only getting 15 pascals, like nothing's going to be accurate there. It's really time to seal some stuff up. But if you're getting close there, like 40, 45, yeah, you can just hit that at button and it'll tell you what that flow would have been if the house could reach 50. So it just gives you a little more leeway in case the house is super, super leaky. We covered this. Yeah, and so I mentioned air changes per hour earlier. If we want to do that, we just tap on channel B and it'll give us this list, say ACH, so we just tap on that. And yeah, anytime we want to go back home, like anytime we get down to the list of settings or something, you can just tap the power button and that'll always take you back to your home screen. So you don't have to keep hitting back. And then this volume icon will appear and you can just tap volume and then you can just enter the volume of the house there. And then that way the gauge will give you ACH in real time. Before we get into house prep, do we have any questions that we need to address in the list?
I think we're doing good. I think
okay.
Keep it rolling and then we'll move on after.
All right, we'll keep trucking. So this is really one of the most important parts and probably the most time consuming part of doing a blower door test is making sure the house is good to go. If we go to the IECC codes, it kind of really lays out some of the best practices. So for example, all windows and doors should be closed but not sealed. Latch the windows, but you don't have to tape over them or anything like that. All dampers should be closed but not sealed off. All interior doors should be open because we don't want to block off any part of the house. We want every part of that house to be able to hit that negative 50 pascals. So we don't want to shut any rooms off like that. Exterior doors for continuous ventilation systems and HRVs or ERVs should be closed and sealed. So this is one that's kind of tricky. So if you have ventilation that runs 24/7, then that's really the only time you can seal something off. It's not very often that you have devices that do that. Usually they're on a timer and only run, maybe 8 hours a day or something like that. There's so many different ways to do ventilation these days. But if it is a system that runs all the time, then you can seal it off. Heating and cooling system should always be off. And then you don't really do anything else with the HVAC system, so no need to tape off returns and supplies and stuff like that, because remember, the ductwork is also part of the envelope. So you want to include any duct leakage into that number. So we want to go check out the crawl space, look for any weird holes or anything like that. We want to check out the attic. We want to look for if there's, and, if this is an existing home, we want to see if there's mold, because if there is mold growth along like a floor or attic or something like that, we don't want to pull that inside. We want to check out the duct system. Anybody ever been to an existing home where they never shut the crawl space door and cats started living in there? It's a nightmare sometimes. So we want to see if anything funky like that's going on. I had a friend that bought a house last year where that happened, and yeah, it didn't take us long to find that. Yeah, doors and windows locked, garage door. People go back and forth on this. I say leave it open. ResNet says leave it shut. But if you want to test at the man door going into the garage, then you can open the door. But you know, typically the garage isn't going to be considered part of the air barrier. But again, it depends on what standards you go by. Some say we want the house in its natural state where the garage door is typically shut. So that's why ResNet says that. But I like to test with it open, just pretend that garage wall is part of the outside. Checking windows, checking doors, checking fireplaces is important. Again, if it's a wood burning fireplace, that's when I like to pressurize and then start at 25 and walk around and just, you know, make sure nothing weird's going on. Combustion appliances, we want to turn those all on the pilot or turn them off. Pilot's okay. If it's a water heater or a furnace, yeah, you can leave it on pilot, and that's okay. But we just don't want any other fans running. We don't want exhaust fans running or dryers running or anything like that. But this next section here, it says for HVAC contractors, but builders, I think, should be just as aware of how air tightness affects HVAC systems, and especially how they're selected in the design phase. Not sure how familiar this crowd is with load calculation software, but when selecting an HVAC system for the home, one of the key inputs that it has to know is infiltration of the home. The house I just moved out of in Raleigh, North Carolina, 20% of the heating load came from infiltration. And if we get that wrong, I mean, that can determine, you know, a couple of sizes. So this is why I say builders should be pretty familiar with this, because you want to be able to review that load calculation and just see where those numbers are coming from. Let's see here. There's some options to choose whether if a house is tight, semi-tight, average, loose, or semi-loose. What a lot of contractors do is just choose average, and because, you know, if they're not going to measure it, then why not? I mean, that's really the justification of it. But it could be loose. Like if you choose loose, they're saying loose is 8CH50, which that's a pretty common number to run into if you're just looking at traditional code homes. I mean, we've seen homes that are 20. And I mean, that's way, way off the scale. So if you don't actually measure and account for that, then you can really get your sizing off. And this can also help you dial in, like really, especially for an efficient home, you want to try to get the smallest system you can. And air tightness testing will justify if you can or cannot do that. I know one of the biggest problems that we see across the country is that there's none of this design that's really happening, and contractors just wing it and get the system way too big. And especially in areas like where I live in the Southeast, a problem with that is short cycling. It runs the equipment out faster, and we can't control for humidity. It gets to the thermostat set point way too fast, and which means the equipment doesn't run long enough to get humidity out of the air. So it just makes houses less comfortable. There's this common misconception that bigger is better, and that's definitely not the case here. So actually having a measured number to input into a load calc just gives you a lot more credibility whenever you choose a system to put into the house. So something to think about. And a question we get to is, at what point is the house too tight? And really, I mean, you get it as tight as you want. You just have to have a good balance between air tightness and ventilation. Airtight homes and mechanical ventilation go hand in hand. When we take away all of our air leakage, we take away that kind of natural ventilation that houses have always had. And so we need a mechanical way to pull some outdoor air in and filter it and control it throughout the day. So all kinds of ways to do that, all kinds of good products out there to do that. But it's important to have a good design for it. And for another one is like who can perform the tests. If you're trying to do it for code, different states have different requirements. But if you're just doing it for quality control, of course, you can just run them yourself and just make sure you're on path with whatever target that you have. And I'm not going to spend too much time on this, but our equipment has evolved quite a bit. There's a couple of testing apps out there now. This one's called rCloud, which will actually geolocate where you are, find the house. You can input certain characteristics about it, and then have a saved report from that specific house that you can always go to later. So if you're like Jake, where you like to do 3 different tests per house, you can have 3 different ports and always go back and see what that progress was for that house. So this is still free to use. You just download it and create an account. You can use a smartphone or tablet. It runs the equipment right from your phone, and then gives you a nice report with a map and has every aspect about the test. The weather that day, uses local weather stations to pull that in. So it's pretty cool, and you can always have access to that information. That's just an example of what the report looks like. And then we have this other one called Gauge Remote, which simply just mirrors the gauge from your manometer to your phone. So this actually has a Wi-Fi antenna in it, so you can connect it on Wi-Fi. And then that way you can walk around and have the controls to your phone, or have the controls to your fan and have a thermal camera on the other hand, and control fan speed without having to run back to the front door to adjust it. So just makes things a little bit easier.
So you can walk around the outside and find the leaks from the outside while the fan's going.
Exactly. Yep. And we have it for PC too. So this is a good training tool. So if you have guys that you're trying to teach this kind of stuff to, it allows you to put our gauge really big on the screen, and you can run through different scenarios and things like that. So I use it when I train people a lot. And then I had a few slides on here about whole house ventilation. This is one we see a lot, where you just have a duct running from the return side of the system to the outside, and it has this kind of air cycler system on it, which is basically a switch and a timer. So if you want 8 hours per day or 20 minutes per hour or whatever, you can set it to do that, and just have the air handler run the fan to bring outdoor air in and run it through a filter before it hits the supplies. I won't get into that today. And as far as finding the leaks, this is the smoke generator that I mentioned before. This is one that we sell. And it's basically just a handheld fog machine where you can go around and spot check different areas. Or if the house is finished, sometimes you can eject it in the middle of the house somewhere, and you can follow it, and it'll kind of take you to the worst area in the house. We just bought a new place in Wilmington, North Carolina, and it led me to a faulty window in less than a minute. So just a way to see what's going on. I doubt that video will work, but we have a larger system for that too, so you can actually smoke the whole house and then go stand outside and see where it's coming from. And I can't not talk about thermal imaging. This is one thing that I want to mention, is that what some people do is just run the door at 50 pascals and then go do their thermal imaging, when really you want to run it at a much lower pressure, because sometimes if you over exaggerate that leak too much, it's hard to tell exactly where it came from. So there's actually a standard that says that the pressure differential should be 20 pascals or less. So this is pictures from my friend Jay Bowen. He's a thermal trainer up in Green Bay area. And so just looking at this one leak from 5 pascals to 10 to 25 to 50, that's just one example. But if you get a more complicated leak in a wall somewhere, if you run it all the way up to 50, it may be difficult to see exactly where it came from. So I usually start around 15 and walk around with my camera, and then have my controls on my phone and bump it up from there if I need to. So just looking at leaks there. But thermal cameras are so cheap now. I mean, you can get a FLIR one for your phone for $500, and for what we're trying to do here, they work fine. I mean, you can you can get good enough pictures to see where your problems are. That's an
provided
attic.
You have the temperature differential. You got to have.
Yeah, you do.
Hot inside and cold outside, or vice versa.
Yeah,
work,
we
right?
recommend at least a 14-degree delta T. You can get away with less sometimes, but usually that's ideal to have at least that. If not, then that's where the smoke testing comes in handy. You can fall back on that. Yep. But yeah, this is an attic knee wall. These are notorious for being super leaky because usually they don't have some kind of rigid backing on the back. Like this house we just got now, I've got to tear into it to get a new attic access and do that. So that's going to be a fun hot summer project that I'm going to do. Where porches tie in, this is a wall with a porch that ties in. A lot of times there's beam pockets leak. So that's what we're seeing there. So any penetration in the ceiling, it just makes these problems visible. So especially if you're working with a client or a homeowner, doors with poor weather stripping. We missed some insulation there and we have a leaky wall. So, and again, this is a 15
door looked
pascals.
like a portal to hell.
Yeah. And that's just at 10 pascals. So yeah. And then finding really small leaks there. Like for example, if we were looking at that wall, if we were just blasting it at 50, it may be really hard to pinpoint exactly where that was coming from. So plumbing stack not sealed through a top plate. So all kinds of problems you can find with thermal imaging. Thermal imaging and blower doors go together really, really well. So when you can exaggerate those leaks, it's really, really easy to make them show up. This is that ceiling grill, return grill that I showed earlier that wasn't sealed. So that's a leak we can see there. Outlets are notorious too. Windows, uninsulated attic hatches, those are easy to get to pop up. You can see if the gas is still left in the window or not. So we can see these top two have expelled. This one's on its way out. This one's still okay. So I'm getting towards the end here. I want to talk about a couple of new things that we have coming out that are going to roll out this year. This is what's called the smart cloth. So this will end up replacing the cloth that comes with our blower door. This actually has tubing stitched into it. So there's no need for the red tube to toss outside anymore. So what this helps is with wind dampening. So when we start a blower door test, we have to do this thing called the baseline test, which allows us to remove the wind factor outside. So you let that gauge balance out for a little while and then take an average, and then it kind of removes that from the equation. It's like zeroing out a scale before you weigh something. So you're trying to remove that wind issue. But sometimes it's hard. On windier days, the less accurate your test is going to be. So what we've done here is put tubing in the fabric itself and branched it out in a couple of locations. And we actually did some tests with it. This is on a day in Washington State where we had some 20-mile-an-hour winds, and the blue dots are the conventional way. The kind of orange dots are with the smart cloth. So you can see that the wind didn't affect it as much as the conventional method. So that's just a new product that we have coming out to try to deal with the wind issue. Because there's never really been a product that's dealt with that, and it's always been a problem. So that's one way we're trying to tackle it. And then this is a new smoke emitter that we're coming out with. So the one that we have now is made by a company called Look Solutions in Germany, and it costs $1,000. So we're making our own and going to sell it at half the price of that. And it's going to be just a handheld smoke gun, and it'll have Bluetooth on it, so you can actually discharge it from other locations. So if you're doing like a mock-up test on a window, you can actually set it inside that test assembly and discharge it from the inside. Or you can put it on an extension pole and get it up like 30 feet if you need to, and still discharge it from your phone. So that's something new that's going to be rolling out this summer. And that's what I've got. We've got a YouTube channel. If you go to YouTube and search Retrotec Energy, we have videos, webinars on all types of topics. So thank you guys for having me on today, and ready to take any questions that might be left over.
Thank you so much for that, Sam. That was very thorough, but also still very concise. I'm kind of excited about the products. It seems like you're kind of looking out for the one-man gang, somebody rolling out that's wanting to run this test.